Hey everyone, welcome to this explainer. Today we're taking a seriously fascinating journey straight into the heart of practical electronics. Our main goal here is to demystify exactly how we control the raw, invisible power of electricity and actually use it to do something as beautifully simple as lighting up an LED. We'll be focusing squarely on the fundamental building blocks drawn directly from Lecture 1 of this incredible course introduction. So we're going to zero in on resistors, voltage dividers, and of course, light-emitting diodes. Let's get into it. So, right off the bat, here's our core problem. I mean, it's one thing to know that electricity exists, right? But it's an entirely different beast to actually use it without completely frying your delicate components. We have to figure out how to take a raw, potent source of electrical energy, carefully step it down, and shape it so it can actually do useful work safely. It's a very physical, immediate problem that we have to solve before we can build absolutely anything. Section 1, the magic of LEDs. Okay, before we get into the heady math and the schematics, let's just appreciate what we're actually trying to power here. Take a look at this mesmerizing array. This is a massive 120 LED setup, emitting a highly intense, broad-angled cyan light. And it's drawing a substantial 25 to 30 watts of power. What's really amazing about this specific design is how it disperses light. As noted in the source material, if you place an LED in water, the light scatters in every direction. Why? Because the plastic casing no longer acts as a lens, thanks to the similar index of refraction between the plastic and the water. This massive array is designed exactly for that kind of broad dispersion. Now contrast that absolute beast of a 30-watt array with this, a single standard red light emitting diode. This tiny building block requires only 1/10 of a watt to operate, and this brilliantly frames a whole challenge. We obviously can't just blast 30 watts into this single component. It would literally go up in smoke in a fraction of a second. So we have to learn how to control and distribute electrical power at the micro level to keep these tiny, delicate components perfectly safe. All right, moving on to section 2, taming voltage with resistors. So to keep that delicate little LED safe, we've got to introduce our very first tool for taming voltage. We can't just plug our components directly into a wall or a large battery. We need specialized components to step down on the power. And this perfectly illustrates how we make the leap from the physical world into the actual language of electronics. You've got the idea of a physical battery, and then its corresponding schematic symbol. Notice how the longer line represents the positive terminal and the shorter line represents the negative. This is basically step 1 in building your circuit literacy, translating real-world power sources into diagrams we can actually analyze. To really wrap our heads around how these circuits behave, we absolutely have to talk about a fundamental rule, Kirchhoff's voltage law, or KVL for short. It states that the sum of the voltage drops going around a closed-loop path is exactly zero. Honestly, just think of voltage like water pressure. If a pump, or in our case a battery, adds a certain amount of pressure to push water up a hill, well, that water eventually has to come down right. The pressure gained has to equal the pressure lost by the time the water returns to the start of the closed loop. And right alongside voltage, we've got Kirchhoff's current law, or KVL. This rule tells us that the total sum of currents entering and leaving a junction equals zero. Going back to our water analogy, this is literally just basic plumbing. The exact amount of water or electrical current flowing into a pipe junction must perfectly equal the amount flowing out. Nothing is lost and nothing just magically appears out of nowhere. Which brings us to section 3, the voltage divider rule. Armed with those two laws, let's check out our most practical tool for taming voltage. This is the exact mechanism you'd use if you needed, say, to make a safe 3 volts out of a 5-volt power supply. It's the classic voltage divider circuit. Notice how we have an input voltage at the top, flowing down through 2 resistors labeled R1 and R2 before hitting ground. The output voltage is tapped right from the middle, right between the 2 resistors. Basically, these 2 components are working together to split the electrical pressure, giving us a usable fraction of the total input. Now, what I absolutely love about these extreme scenarios is how they give you instant intuition without forcing you to sit there and memorize complex algebra. Like always evaluating the extreme cases, you intuitively understand the circuit. Like if the top resistor, R1, goes to infinity, meaning it's essentially a broken wire, your output drops to 0. If R1 and R2 are identical, well, they perfectly split the voltage right down the middle, in half. These simple rules of thumb let you visualize the circuit's behavior at a total glance. Okay, let's actually test that intuition out on a real-world example. Say we had a 9-volt source going through an 80 ohm resistor and a 10 ohm resistor. According to the source material's rule of thumb, the output voltage always stays closest to the voltage at the other end of the lower valued resistor. Since 10 ohms is way lower than 80 ohms, the output is going to be pulled very close to the ground voltage at the bottom. And in this specific case, it pulls it all the way down to just 1 volt. Let's dive into section 4, diodes, the one-way valves. All right, so we figured out how to wrangle our voltage. Now we really need to look closer at the actual component we're trying to light up, the diode. Here is the schematic symbol for an ideal diode, featuring a flat line and a triangle. The top is the positive anode, and the bottom is the negative cathode. And hey, if you're ever trying to remember which is which, the source notes a super cool historical trick. Electrons actually come from the cathode, much like how cathode rays were emitted to hit a screen in those old heavy CRT television tubes. Kinda neat, right? The actual job of an ideal diode is honestly incredibly straightforward. Think of it as a strict gatekeeper or a one-way check valve if we go back to our plumbing analogy. If freeway allows current to flow down in the direction of the arrow, if current tries to reverse and flow upward, the diode completely blocks it. Absolutely no current flows backwards. But here's the thing. Our LED isn't just a basic one-way valve. It has a very specific behavioral quirk. Check out this plot. A standard resistor shows a nice, steady, sloping line. As voltage goes up, current goes up proportionally. But the diode, which is that dotted vertical line, does absolutely nothing until it hits a very specific forward voltage. Once it hits that exact voltage, boom, it suddenly turns on, allows current to flow, and fiercely holds the voltage exactly at that level. And that brings us to section 5, powering your first circuit. Let's see how all of this builds into our grand finality. What did it take everything we just learned about voltage drops, resistors, and diodes, and design a safe, fully functional LED circuit entirely from scratch? Let's just walk through this logically, step by step. We start with a strong 9-volt battery. We know from our plot that the LED will turn on and firmly hold a 2-volt forward voltage. Now, because of Kirchhoff's voltage law, remember what goes up must come down, that remaining 7 volts has to be absorbed by our resistor. Using a 700 ohm resistor, we just divide 7 volts by 700 ohms, and that gives us a gentle, perfectly safe 10 milliamps of current. So the really crucial takeaway here is this. By pairing that 700 ohm resistor with our diode, we successfully tamed a 9-volt battery. We stepped the pressure down, restricted the current, and safely powered the LED without burning out. You have literally just proven that you can confidently combine these fundamental principles to piece together functional, practical electronics. You now officially possess the basic vocabulary of circuits. You understand exactly how resistors split voltage, how Kirchhoff's laws balance the entire system, and how diodes lock voltage down while acting as one-way valves. You've seen the math work intuitively, and you've seen a circuit come to life. The tools are well and truly in your hands now. So, knowing how to tame voltage and control light, what will you build next? Thanks so much for joining me for this explainer, and keep exploring.